So we can actually set up I, J, K, and I just repeat it. If I'm going in that direction, I get a positive answer. So I cross J is K, J cross K is I, K cross I is J. Didn't do that one, but K cross I, so I have K coming out, I is that way. My result is up in the J direction. So those are positive torque, or positive cross products. Going in this direction, negative. J cross I is negative K. I cross K is negative J. K cross J is negative I. So if you go in order of I, J, K, and then sort of around the corner, it's positive, opposite direction, negative. So if I had 5 I hat plus 2 J hat cross 3 I hat minus 4 K hat, well, I cross I, I'm foiling now. I cross I is
Hat squared.
that'd be I dot I. What's I cross I?
Just like I cross I, like over here with the like I cross J.
That'd be like saying, what's 1 plus 2? Well, that's 1 plus 2. Yes, that's a true statement, but
Is it
not where we
zero?
need to get to. Pardon?
Is it 0 as well?
It is 0, because what's the angle between
0.
sine of 0 is 0. So I cross I is 0. I cross K,
Oh, negative J?
Yeah.
yeah. So I have 5 times negative 4, which is negative 20, times negative J, plus, now inner, J cross I,
Negative K?
and then last, I have negative 8 is the math piece of, or the normal math, and J cross K.
Is I.
I.
So my final answer is, in order of IJK, negative 8 I hat, plus 20 J hat, minus 6 K hat.
What does that tell us? Like, what is that?
It's just showing how to multiply using the rectangular coordinate system. I didn't give any physical context to this. If this were a force and this were the moment arm, that would be the torque. Oh, wait, no, strike that. If that's the moment arm and that's the force, order doesn't matter. This would be the direction of the torque, which is actually perpendicular to how your hand would move. Three-dimensional problems like this are really nice in terms of just abstract board stuff. It's not particularly easy to, well, that'd be obviously going in that direction. All right, so we've gone through at least a simple example of that. Let's actually apply this.
The record, this is not how I was taught multiplication in elementary school, just to comment on your
Oh.
earlier.
They did it differently?
Yes.
Okay. If you throw a block through the air and it rotates, let's make this 10 meters long. Let's give this a mass of, let's make it a uniform beam. Mass of 50 kilograms. So I have a beam being held up by two ropes. uniform beam, 50 kilograms, 10 meters long. The left rope is, we'll make this 2 meters from that side, and this will make 7 meters from the left side. What is the tension in each rope? Now, before we got to the rotational stuff, this would not be a problem that would have been within the realm of solving, because you have two unknowns and we have only one equation if F equals ma. But we now can come up with a second equation. I'm going to establish a coordinate system, I hat, the same right-hand coordinate system, k hat. We have a j hat equation, and we have a k hat equation. There's no I hat equation, there's no forces or any torques, or there's no rotational stuff happening horizontally. For the sake of writing, because I really, writing the subscripts becomes a nuisance, I'm going to call this A, and I'm going to call that B. If we did the force diagram, we have weight acting down on the middle of this thing. And let's make G equal to 10 meters per second squared. Some strange world that would be completely foreign to us. What is the weight of the beam?
50 kilograms. No, sorry. 500. 50 times 10, right?
500 what?
Wait.
You do it. Kilogram meters per second squared is not just newtons?
It is just newtons.
Yeah.
500 newtons.
Okay.
Or you could have gone with kilogram meters per second squared. But. So I got 500 newtons acting down. So I plug in the F equals ma. Let's make, up is positive, that's j hat. So my j hat equation, I've got A plus B minus 500 is equal to mass times the acceleration of 0. Oh, I guess I should go ahead and state that just sitting there.
As instead of equilibrium?
Yeah. Static equilibrium, and yeah, that should actually cover it. Which means that not only is it not moving up, down, left, or right, it's also not spinning. It's in rotational equilibrium as well. Rotational equilibrium, angular acceleration is 0, total torque is 0, angular velocity doesn't change. The same stuff we were saying before, except now we just throw the fancier new word into it.
Wait, can I clarify that?
Yes.
So when you said static equilibrium, did that also cover rotational equilibrium, or are they separate?
I was originally considering them as separate and thinking that it should be called static rotational equilibrium. However, static means not moving, and so if it's not moving, it can't be rotating also.
Right. Okay.
So we can always assume if it says it's in static equilibrium, that it's also not spinning.
Correct. Now for the k hat equation, we can't use F equals ma because there are no forces in and out of the board, but there is torque. And so we look at torque is equal to I alpha for my k hat equation. I have 3 forces acting on the beam. So potentially I have 3 torques. So I have weight going down, I have A going up, and B going up. In terms of distances, from the left-hand side, that's 2 meters, that's 5 meters, and that's 7 meters. Now, if I'm dealing with a door, the axis of rotation is naturally at the hinge. But if I'm dealing with something that's not moving, what is the axis of rotation?
The center of the beam?
Sure. Or?
Wherever you said it?
Yep. Brooks, go first, so let's go with that one. So we're gonna make this our axis of rotation, because Brooke says so. So, vector A there, the force A, which way is that trying to rotate the beam?
It's pulling up on the beam, so.
Okay,
Clockwise, I guess.
But it's not moving.
it's not, I said, which way is it trying to rotate it? So, well, we
Clockwise
can do better
around
than
the-
Right.
clockwise.
Into the board.
Yeah, if that's my axis right there, force A is trying to rotate it around like that, in the negative K direction.
Oh.
So I have negative, a couple ways we can do this. We already know the direction, it's negative K. My moment arm here, what's the length of my moment arm?
3 meters.
Wait. Yeah,
Pardon?
3.
Yep, so it's negative 3A. My moment arm times my force. The direction, we thought through the direction, so we don't have to worry about bringing in sign of anything.
And the moment arm is always positive because it's just a length. It's the,
I hesitate to say always positive.
okay.
The magnitude is always positive, the negative sign, if there's one in there, would indicate direction.
Okay,
How do you know that it's, like the length from the center of the like axis of rotation? Like you.
But the moment arm is always from the axis of rotation to where the force is applied.
Right.
Now, it's from the center here because you said, that you suggested first to make that the axis of rotation.
Are you following like a formula over here though, like with K hat? Are you like, is this like a formula to like negative 3A?
All right, all the forces are perpendicular to the beam.
Right.
Torque is R cross F. So the magnitude of the torque is RF sine of theta. In this particular case, theta is 90 degrees. So that's gonna be equal to 1. So the magnitude of my torque is just RF. So that's where, so I'm just, that's 3 is R, the force is A.
Okay. Doesn't R stand for like rotational vector though? Wait,
Radial.
okay. That makes more sense, okay. Thank you.
Now we move on. Second force. The weight, 500 newtons. What is the length of the moment arm here?
0.
Plus 0 times 500. And then B here. What is the moment arm?
2
2,
meters.
B,
And the direction of the torque?
It's towards us, so negative K.
positive K hat?
And fight. So if that's my axis, so imagine I've got my beam right here, and I got a force acting up this way. Which way is that trying to make this thing rotate?
Counterclockwise.
Trying to make it rotate around like that,
Versus.
which is the K hat.
which is the K hat
Positive
direction,
K hat, right?
the positive K hat.
It's a verb thing.
Right.
Equals the moment of inertia, which I haven't told you how to find yet, times the angular acceleration, 0. So mathematically, so physics gets us that far, now the math problem kicks in. Let me just write the math problem down. The math problem is A plus B equals 500, and negative 3A plus 2B equals 0. 2 equations, 2 unknowns. How you solve it is up to you. I'm going to solve for B and plug in. So from this equation right here, I have 2B equals 3A. B is equal to 1.5A. Thank you. And so plugging into the first equation, I get A plus 1.5A equals 500. 2.5A is equal to 500. A is equal to 200. And therefore B equals 800. Let's take a moment just to see if this makes any sense whatsoever. I have a beam here. The right-hand side is closer, this is 2 meters here, and this is 3 meters here. So I would expect the right-hand side to be exerting more force than the left-hand side. It's closer. If that were directly there in the middle, it would take all of the force. So the closer it is to where the other force is applied, the more force I'm expecting it to take. And we got 300 newtons here and 200 newtons here. So in that sense, it makes some sense.
How did you get the -3A?
From the direction, we're doing a k-hat equation here, and in this particular case, this was selected as the axis of rotation. Force A is, so my axis of rotation is in the middle there. Force A is up on this side and is trying to get it to rotate. I guess from your point of view, that'd be clockwise, which rotates like that. My thumb points towards the board. I said, oh, there it is. Right here is where I said out of the board was positive K. So into the board would be negative K. That's why that negative shows up.
Why is it 3?
Moment arm times the force times the sine of the angle between them. The angles, these are all 90 degrees here, so the sine of 90 degrees is 1. So it's just R times F. R is the distance, magnitude of the radial moment arm from our axis of symmetry to where the force is applied. It's a uniform beam, so there's 500 newtons we are treating as acting straight smack dab in the center, 5 meters from the left edge. This is 2 meters from the left edge, so therefore that's 3 meters between them. That's where the 3 comes from. All right, other questions right now? Because I'm about to solve the exact same problem again.
Without running through it, would we get the exact same values for A and B if we had set the axis of rotational symmetry or whatever?
Axis of rotation.
Axis of rotation to a different point on the beam?
Let's find out, because that's exactly what I was going to do next. Great minds, thinking alike. What do you want to pick this time?
Let's do the extreme end on the left side of the beam.
All right, so making this the axis.
Yeah.
Because Anna said so.
This.
Pass.
Thanks.
Now A is trying to rotate it, B and A and B are both trying to rotate it in the positive k-hat direction. The weight is trying to rotate it in the negative k-hat direction. So we still have A plus B is equal to 500. That hasn't changed. The second equation becomes, so that's 2A minus 5W plus 7B equals 0. I know that the weight is 500 newtons. So this becomes 2A plus 7B is equal to 2,500. Because that's 2,500 and I added to both sides. Solve for A. A therefore is equal to 2,500. Well, 2,500 minus 7B divided by 2, which is 1,250 minus 3.5B. Plug that into there. And so I have 1,250 minus 3.5B plus B, that's A right there, is equal to 500. 1250 minus 2.5b equals 500. Bring this over, I get, or actually, swap like that. 750 is equal to 2.5b. 2.5 is equal to 300.
What happened
Wow,
to
that
your-
is horrible notation there. There we go.
What happened to your other B? Like you went from, wait, never mind, cause that's A plus B.
So this is what I saw for A right there.
Right.
If I plug that into here,
You get that, right?
that's my A
Plus B.
plus B.
Where did that B go?
This is now, negative 3.5b plus b is negative 2.5b.
Oh, okay, thank you.
Is it supposed to be the same?
Yes, it should be. Matter of fact, the axis of rotation doesn't even have to be on the beam. I can make the axis of rotation, 10 meters that way. There's no advantage to doing that, but I could have. In this problem, there's no advantage. I'm gonna solve it one more time, except with less math. Any other questions on the left end being the axis? I'm now gonna choose that as my axis. The reason of this. We still have the same J-hat equation. That still hasn't changed. Axis of rotation has nothing to do with the linear forces. So I still have A plus B is equal to 500. My torque equation, what is the torque that A will exert about that pivot point?
0.
Right, so I'm not even gonna bother writing it down at this time. Before I wrote, the 0 times 500, but it doesn't contribute to anything other than I'm leading towards more environmental damage by using the ink. So what I end up with is, well, the weight is trying to rotate it with the negative, in the negative k-hat direction. So I have negative